Today we're going to be solving May-June 2023, paper 42. Question number 1 says, group 2 carbonates decompose when heated to form the metal oxide and carbon dioxide. Suggest a mechanism for the decomposition of the carbonate ion by adding two curly arrows in figure 1.1. Now over here the carbonate ion decomposes to form carbon dioxide and the oxide ion, right? Now carbon dioxide is a carbon which is double bonded to two oxygens, right? So what we have to show here is the formation of a second double bond. We have to show the formation of a second double bond and the removal of an oxygen to form the oxide ion. Now how does the second double bond form? Well, they've conveniently drawn a lone pair for us, right? That lone pair, we're going to show a curly arrow from the lone pair to this bond, so that means that that becomes a double bond, and then obviously this oxygen will take away both of these electrons. This oxygen will take away both of these electrons, and we'll end up with the oxide ion. We'll end up with the oxide ion. So that's the decomposition of the carbonate ion to carbon dioxide and oxide ions. Describe the variation in thermal stability of group 2 carbonates. Explain your answer. This is a very common question, right? The thermal stability increases down the group. The thermal stability increases down the group, right? The reason why is because the cationic radius increases, or the radius of the cations increases. Therefore, the charge density and polarizing power of the cations decrease. Hence, there is lesser polarization of the anion. Hence, there is lesser polarization of the anion. In this case, that would be the carbonate ion. Define lattice energy. This is another commonly asked question, right? Is the energy released? Here is the energy released when 1 mole, of an ionic solid is formed from its constituent gaseous ions. Is formed from its constituent gaseous ions under standard conditions. Constituent gaseous ions under standard conditions. Okay, the ionic solid being formed is going to be formed under standard conditions. Okay, so the ionic solid has to be in a standard state. Okay, in that case that would be a solid, right, at 298 Kelvin and 1 atmospheric pressure. Part 2 says the lattice energy of the group 2 carbonates becomes less exothermic down the group. The lattice energy of the group 2 oxides also becomes less exothermic. The lattice energy of the carbonate and the oxide change by different amounts going down the group. Suggest how the standard enthalpy change of the decomposition reaction for group 2 carbonates changes down the group. Explain your reasoning in terms of the relative sizes of the anions and the relative changes in lattice energy down the group. The first thing we have to answer is how the enthalpy change of decomposition changes down the group, right? Now we know that the thermal stability of the carbonates, increases down the group. In other words, it's more difficult for them to decompose, right? More difficult for them to decompose, or higher temperatures needed for decomposition. So that means down the group, right, the enthalpy change of decomposition, okay, becomes more endothermic, okay? In other words, more heat or a higher temperature is required for decomposition. The enthalpy change of decomposition becomes more endothermic, okay? Now we have to explain why it becomes more endothermic in terms of the lattice enthalpies of the carbonate and the oxides. Now, the way to think about this is the lattice enthalpy, right? The lattice enthalpy is a measure of the energy, okay, the relative energy of a solid, okay? In other words, the more exothermic it is, okay, the more exothermic it is, right, the more exothermic it is, the more stable the solid, okay, more stable solid, okay. So down the group, what's happened to the stability of the carbonates? The carbonates are becoming more stable, right? The carbonates are becoming more stable down the group, okay, they're more stable down the group. If they're more stable down the group, that means that the lattice enthalpy for the carbonates is relatively more exothermic, okay. Again, if the lattice enthalpy is more exothermic, it means that the solid is at a lower energy, right? Because we're going from gaseous ions, right? We're going from gaseous ions to solid lattice, right? And that's an exothermic change. And what we're saying here is that the more exothermic the lattice enthalpy, the more stable the solid. We know that down the group the carbonates are, more stable, which means that the lattice enthalpy of the carbonates is relatively more exothermic. Okay. And down the group, right, the lattice enthalpies are becoming less exothermic for the carbonate and the oxide. They're becoming less exothermic for the carbonate and the oxide. However, the carbonate's lattice enthalpy remains relatively exothermic. It remains relatively exothermic, which means it's not changing that much. Down the group, they're becoming less exothermic, but the carbonates isn't changing that much, which is why it remains relatively more exothermic. So it's not changing as much as the lattice enthalpy of the oxides. It's not changing as much as the lattice enthalpy of the oxides. So over here we can say that the lattice enthalpy, okay, the lattice enthalpy of the oxide changes by a greater amount. Okay, changes by a greater amount. Okay, than lattice enthalpy of the carbonates. Okay, and we have to explain this in terms of the relative sizes of the anions. Okay, over here we can say then that's because the oxide ion, okay, the oxide ion is smaller than the carbonate ion. Okay, is smaller than the carbonate ion. Okay, potassium sulfite K2SO3 is used as a food additive. The concentration of sulfide ions can be determined by titration using aqueous acidified manganate 7 ions. A 250 cm3 solution contains 3.4 grams of impure potassium sulfide. Okay. We have a 250 cm3 solution of impure potassium sulfide. 25 cm3 of this solution requires 22.4 cm3 of 0.025 moles per dm3 manganate 7, acidified manganate 7 to reach the endpoint. All the sulfide ions are oxidized. None of the other species in the impure potassium sulfide are oxidized. The reaction occurs as shown by the two half equations. Give the ionic equation for the reaction with sulfide ions and acidified manganate 7. To get the ionic equation, we need to first balance the electrons in the two half equations. Here we have 2 electrons, here we have 5 electrons. So we can multiply this equation by 5, multiply this equation by 2, right? So what do we end up with? We get 5H2O, we get 5SO3 2 minus, we get 5SO4 2 minus, we get 10H plus, and then we get 10 electrons. And at the bottom we have 2MnO4 minus, 16H plus, 10 electrons, and then we have 2Mn2 plus and 8H2O. Okay, we're going to cancel out the electrons. Okay, cancel out the electrons here. We have 5H2O on the left, we have 8H2O on the right. 5H2O, 8H2O, right? So we're going to have 3H2O over here. Okay, we're going to have 3H2O over here. On the product side, right? Because the net is 5 and then we have 8. So we have 3 more on the right hand side. Okay, we have 5SO3 2 minus. We have 5SO3 2 minus. We have over here we have 2MnO4 minus. Okay, so we have 2MnO4 minus. Okay, we also have 16H plus here, we have 10H plus here. 16H plus, 10H plus. So that means we have 6 more H plus on the left, right? We have 6 more H plus on the left. So we're going to have 6H plus. We're going to have 6H plus here. And then for the products, we have 3H2O. Okay, we've already done the H2O here. Okay, we've already done the H2O. We have 2Mn2 plus and we have 5SO4 2 minus. Okay, 2Mn2 plus and 5SO4 2 minus. 5SO4 2 minus. Calculate the percentage purity of the sample of potassium sulfite. So in these types of questions, the first thing you want to do is find the moles of the titer. Right here, they've told us the volume and the concentration of the manganate 7, right, that was needed to reach the endpoint. So we can say that the number of moles of manganate 7, MnO4 minus, is the concentration times the volume, which is 0.025 moles per dm3. That's the concentration. The volume is 22.4 cm3, so we divide that by 1000. We get 5.6 into 10 to the power of negative 4 moles. Okay, so that's the moles of manganate 7. Okay, because we want the purity of potassium sulfide, we can find the moles of sulfide from the molar ratio. So we can say over here that for every 2 moles of manganate 7, okay, for every 2 moles of manganate 7, 5 moles of potassium sulfite are reacting, right? We have a 2:5 ratio, 2:5 ratio. So we have 5.6 into 10 to the power of negative 4 moles of manganate 7. How many moles do we have of sulfite? We can just cross multiply. That gives us the number of moles of sulfite as 1.4 into 10 to the power of minus 3 moles, right? Now this is the number of moles in 25 cm cube of the original solution, right? That's the solution that was titrated against, right, with the manganate 7. So this is the number of moles in 25 cm cube, right? So that means in 250 cm cube in the original solution, we have 10 times the number of moles. Okay, we have 10 times the number of moles because only 1/10 of that solution was taken for the titration. Okay, so in the original solution, we have number of moles of sulfite is 1.4 into 10 to the power of negative 2, right, in 250 cm cube. Again, all I've done is I've multiplied this by 10, right? So now we have the number of moles of sulfite in the original solution. So we know the number of moles of potassium sulfite. Okay, we know the number of moles of potassium sulfite, and we know the mass of the impure potassium sulfite. So over here we can say that our impure potassium sulfite was 3.4 grams, right? So 3.4 grams was the impure sample. We know that in this, the pure potassium sulfite is 1.4 into 10 to the power of minus 2 moles, right? 1.4 into 10 to the power of minus 2 moles. So we can say that the mass of potassium sulfite is equal to the number of moles times the molar mass. So the number of moles is 1.4 into 10 to the power of minus 2. The MR of potassium sulfite is 158.3. Okay. 158.3, you can calculate that using the periodic table. And what you end up getting over here is 2.2162 grams. Okay, 2.2162 grams. So that means the percentage purity is 2.216. 2 grams divided by 3.4 times 100. That comes out to 65.2%. So that's the percentage purity of the potassium sulfite. Potassium disulfite is another food additive. The disulfide ion S2O52- has the displayed formula shown in figure 1.2. Reduce the geometry around this sulfur atom in S2O52-. This is the alpha sulfur atom. So what do you think the geometry around the sulfur atom is? Sulfur has 6 valence electrons, all of them are bonded. You have 4 atoms, no lone pairs. So if you have 4 atoms around a central atom, what's the geometry around that central atom? The geometry is tetrahedral. Okay? Geometry is tetrahedral. Again, you have 4 atoms bonded to this sulfur. Right? You have 4 atoms bonded to the sulfur and all 6 valence electrons are bonded. So there are no lone pairs, right? If you have 4 atoms bonded and they're distanced or spaced out equally, that means that that sulfur has a tetrahedral shape. Question number 2 says state 2 typical chemical properties of a transition element. So one typical chemical property is that transition elements have variable oxidation states. They have variable oxidation states. Okay, they form colored compounds. They can behave as catalysts. Okay, so you can write any of these. They can behave as catalysts. They have variable oxidation states. They form colored compounds, they form complex ions, and so on. And what's a complex ion? A complex ion is a species that consists of a central metal atom, okay, a central metal atom or ion bonded to one or more ligands, okay, bonded to one or more ligands. Samples of cobalt-2 hexaaqua, the COH2O62 plus, are reacted separately with an excess of aqueous ammonia, with an excess of concentrated HCl, and with an excess of aqueous sodium hydroxide as shown in figure 2.1. Complete table 2.1 about the reactions shown by this complex ion. Now when aqueous ammonia is added to this guy, okay, what we get is cobalt-2 hexaamine, okay, which is CONH36, okay, and then this guy has a charge of 2 plus. What we observe is a brown solution. We observe a brown solution, okay, and the state therefore must be aqueous, right? We have an aqueous solution, okay, and the type of reaction is a ligand exchange reaction, okay, it is a ligand exchange reaction. When excess of concentrated HCl is added, you get cobalt-2 tetrachloride, so COCl4, 2 minus. This is a blue solution. The type of reaction again is a ligand exchange or a ligand substitution reaction. Okay. The word solution implies that it's aqueous, which you can mention aqueous. Okay. Excess of aqueous sodium hydroxide, you get a precipitate, right? It's a precipitation reaction. You get cobalt-2 hydroxide. They would accept this as an answer, but the proper answer is this. Okay, 2 of the water molecules are replaced by hydroxide ions. Okay, and what you end up getting is a blue precipitate. Okay, so blue precipitate. Now again, you can say precipitate or you can say solid for the state. Okay, the word precipitate implies solid, so you don't have to say solid. And the type of reaction, it is a ligand exchange, but we specify this as a precipitation reaction. Okay, when a precipitate forms, you have to specify it as a precipitation reaction. The ethane dioate ion can act as a bidentate ligand. Explain what is meant by a bidentate ligand. A bidentate ligand is a species that donates two lone pairs. Okay? It donates two lone pairs of electrons to form two dative covalent bonds or coordinate bonds. Okay, two dative covalent bonds to a central metal atom. Okay, to a central metal atom or ion. The complex CO H2O twice C2O4 BrCl minus exists as stereoisomers. Complete the three-dimensional diagram in figure 2.2 to show four stereoisomers of this particular complex. The C2O4 minus, the ethane dioate ion, is represented using this. Okay, so they've already drawn this. They've already drawn this bidentate ligand over here. Okay, they've already drawn this guy over here. So we're only concerned with the two water molecules and the Br and the Cl. Okay. Now, the way to think about this is first think about the possibility that the two water molecules are bonded 180 degrees from each other, right? That's one possibility. The two water molecules are bonded 180 degrees from each other, like this. And then you're left with a Br and a Cl. Now, another possibility is the two water molecules are bonded 90 degrees to each other. Okay, the two water molecules are bonded at 90 degrees to each other, like this. That means that the Br and the Cl are opposite each other. Okay, like this. So these two are obviously geometric isomers of each other. Well, over here, what we've shown is that we've shown the two water molecules directly opposite this bidentate ligand, right? We've shown the two water molecules directly opposite this bidentate ligand. Another possibility is that the two water molecules are 90 degrees from each other, like this, but not both of them are directly opposite this bidentate ligand. Okay, so you have to think a little bit over here. Okay, this is not one of those common cases of isomerism, but the idea here is that first we think about 180 and 90 degrees, then we think about their positions relative to the bidentate ligand. So here both the water molecules are directly opposite the bidentate ligand. They could be at 90 degrees, but not directly opposite the bidentate ligand. So then we're left with Br and Cl over here. And then we can draw the same thing. So we can draw the same thing like this, but instead of showing the bromine opposite the bidentate ligand, we can show the chlorine opposite the bidentate ligand. Okay. So these are 4 stereoisomers, okay, for this particular complex. One thing you guys should be careful about is drawing the oxygen from the water bonded directly to this cobalt. Okay, please do not show this bond to the hydrogen. Okay, do not show this bond to the hydrogen. Show it to the oxygen. Okay, in all of these cases, I've shown the bond to the oxygen atom. State the oxidation state of cobalt in this complex and a type of stereoisomerism shown. A type of stereoisomerism. So A type of stereoisomerism shown is geometric, right, as we just mentioned, right? We have cis-trans isomers here. The two waters are 180 degrees. Here they're 90 degrees. So this is the cis isomer. This is the trans isomer. And then for the oxidation state of cobalt, right? Let's say that cobalt is X. We know H2O has an oxidation state of 0, right? This C2O4 is 2 minus, so that's minus 2, right? We have a Br and a Cl, so that's the bromide ion, which is minus 1. We have a chloride ion, which is minus 1. And then the overall oxidation state is negative 1, which gives us X as positive 3. So the oxidation state of cobalt is plus 3. So here we have question number 3. Just complete table 3.1 by placing one tick in each row to indicate the sign of each type of energy change under standard conditions. The bond energy is always positive, right? By definition, it's the energy needed. The energy needed means the energy taken in, right? The energy needed to break 1 mole of covalent bonds in the gaseous state. Enthalpy change of atomization is also always positive. The enthalpy change of formation is usually exothermic, but it can also be endothermic. So it can be positive or negative. Okay. Define the standard enthalpy change of atomization. The standard enthalpy change of atomization is the enthalpy change. It is the enthalpy change when one mole of gaseous atoms, okay, when 1 mole of gaseous atoms are formed from the elements in their standard state. Okay, from the elements in their standard state. From the element in its standard state. Okay. Table 3.2 shows some energy changes. So we're given a table with these energy changes over here. Calculate the lattice energy of silver oxide using relevant data from table 3.2. It may be helpful to draw a labeled energy cycle. Show your work. Okay, so we're going to use this data over here and take this table, go back down for a second, right? I have to calculate the lattice energy of silver oxide. The best thing to do is to start with the elements, okay? The best thing to do is to start with the elements. So we have Ag plus O2, right? We have silver solid, oxygen gas, right? In Ag2O, okay, the lattice energy is the enthalpy change when 1 mole of silver oxide is formed from the constituent gaseous ions, right? We want 1 mole of this, that means we're going to need 2 moles of silver, right? We need 2 moles of Ag, and we need half a mole of O2, right? Because we have just one oxygen atom. Okay. Now usually I like to start with the enthalpy change of formation. So I start with the elements. The enthalpy change of formation is given to us, right? The enthalpy change of formation here is negative 31. So that will be a downward arrow. Okay. Downward arrow negative 31. We have Ag2O solid, right? That's the enthalpy change when 1 mole of a substance is formed from its constituent elements. Okay. And now we're going to complete the rest of the cycle. So we're first going to start with silver. Okay, it doesn't matter which one you start with. I'm going to go with silver. So first we're going to convert silver to its gaseous atoms. That would be the atomization of silver. So we have 2 moles of silver. So that would be 2 times the atomization. Okay, 2 times the atomization of silver. Okay, so what do we have here? We have 2 Ag gas. Okay, we have 2 Ag gas plus half O2, right? 2 times the atomization of silver. Then we have 2 times the first ionization energy, right? We have 2 times the first ionization energy of silver, right? So we end up making gaseous silver ions. We have 2 Ag plus gaseous, and then we have half O2, right? So again, we want to get to the gaseous ions because the lattice enthalpy is gaseous ions to solid lattice. So we're going to convert the elements to the gaseous ions. We convert silver to its gaseous ions. Now we're going to talk about oxygen, right? So first we have the bond enthalpy of oxygen. We have half the bond energy, right? We have half the bond energy of oxygen, right? Half the bond energy of oxygen. We have half a mole of oxygen molecules. So over here we end up with 2 Ag plus gaseous, and then we have gaseous oxygen atoms, right? And then we need to add electrons to the oxygen atoms, right? Because we want to make the anion of oxygen. So we have the first electron affinity, and we have the second electron affinity. Okay, first electron affinity and the second electron affinity. So the first electron affinity is exothermic, right? The first electron affinity. The electron affinity is the enthalpy change when 1 mole of electrons are added to 1 mole of gaseous atoms to form 1 mole of gaseous 1 minus ions. So we have 2 Ag plus gaseous plus O minus gaseous, and then we have the second electron affinity. Okay? We have the second electron affinity, which is usually endothermic, right? Which is always endothermic, rather, I should say. Okay, and then we have our gaseous ions. Okay, we have 2 Ag plus gaseous and then O2 minus gaseous. Okay, you don't have to write each of them individually. You can also group them together. Okay, you can also group these enthalpy changes together if you want. And then lastly, of course, over here we have the lattice enthalpy, right? The lattice enthalpy would be from the gaseous ions to the solid lattice. Okay, from the gaseous ions to the solid lattice. So that would be the lattice enthalpy, which is what we have to find. That would be X. Okay, so now we're going to plug these values in, right? The atomization of silver is somewhere here, 285. So we have 2 times 285. The first ionization energy of silver is 731. So 2 times 731. The bond energy of oxygen is 496. So we have 1 half times 496. The first electron affinity of oxygen is negative 141, and then the second electron affinity is positive 798. So negative 141, positive 798, right? So now we have our Born-Haber cycle, right? Now we just have to add these values together. So what do we get? Well, if we use the cycle over here, what we have is this, right? In a different color, we have 2 times 285 plus 2 times 731 plus 1 half times 496, right? So we're saying that we're going in this direction, right? 2 times 285 plus 2 times 731 plus this, plus this, plus this, and then plus this, all the way this is equal to negative 31. Okay, this is equal to negative 31. So we're saying we're starting with the elements, and ending up with the solid lattice. We can go the long way around, convert the elements to the gaseous ions and then get to the solid lattice, or we can go directly from the elements to the solid lattice, right? That's basically Hess's law. So here we have 2 times 285 plus 2 times 731 plus 1 half times 496 minus 141 plus 798 plus X, and this is equal to the enthalpy change of formation. And this gives us the lattice enthalpy, which is X, as negative 2968 kilojoules per mole. Suggest the trend in magnitude of the lattice energies of the silver compound silver sulfide, silver oxide, in silver selenide. Okay. Now here the strand that they're talking about is going down the group, right? Going down the group. What would happen to the lattice enthalpy as you go down the group? You have oxygen and then sulfur and then selenide, right? What would happen to the lattice enthalpy as you go down the group? Down the group, the ions are going to get larger, right? So we have oxygen, sulfur, and then selenium. So that means that over here, the most exothermic will be the lattice enthalpy of silver oxide, right? Because the smaller the ion, the stronger the forces of attraction, the more exothermic the lattice enthalpy, right? The stronger the attraction, the more exothermic the lattice enthalpy, right? More energy is released when ionic bonds form. So smaller ion, more exothermic lattice enthalpy, and the least exothermic will be for silver selenide. Okay? And then silver sulfide is going to be in the middle. The explanation is that obviously down the group, right, the size of the anion increases. Okay, the size of the anion increases down the group. Therefore, the charge density decreases. Hence, the ionic bonds become weaker. Okay, the ionic bonds become weaker. Silver sulfite is sparingly soluble in water. Give an expression for the solubility product KSP of silver sulfite. Okay, so we have silver sulfite Ag2SO3. Okay, I'm going to write this down. We have 2Ag plus, and then SO3 2 minus. Okay, these are aqueous, so this is solid, aqueous, and then aqueous, right? And then for this, for the KSP expression, we have the concentration of Ag plus, the whole thing squared, right, to the power of the stoichiometric coefficient, times the concentration of sulfite. The next part says, calculate the equilibrium concentration of silver ions in a saturated solution of silver sulfite. The concentration of a saturated solution is also referred to as the solubility. Okay, the concentration of a saturated solution is also referred to as the solubility. So we have the salt over here, right? And the solubility is again the concentration of a saturated solution. So let's say x moles per dm cube of silver sulfide dissolve. Okay, x moles per dm cube of silver sulfide dissolve, which means you're going to have 2x moles of silver ions and x moles of sulfite ions, right? Because again, the solubility is the concentration of a saturated solution. That's the amount that dissolves per dm cube, right? So if x moles of this dissolves, then you get 2x moles of silver, because 1:2 ratio. You get x moles of sulfite, right? The KSP expression is the concentration of silver squared. So 2x, the whole thing squared, times the concentration of sulfite, and this is equal to the KSP. That's 1.5 into 10 to the power of negative 14. Okay, so you get 4x cubed is equal to 1.5 into 10 to the power minus 14. And that gives you x, which is the solubility or the concentration of the saturated solution, as 1.55 into 10 to the power of negative 5 moles per dm cube. Right, so that's the concentration of silver sulfite, right, in the saturated solution. We want to find the concentration of silver ions. That's 2x. Okay, so that means the 2x is obviously just 2 times this value. Okay, so we get 2x as 3.11 into 10 to the power of minus 5 moles per dm cube. Okay, that's the concentration of silver ions. So that's the concentration of silver ions. The standard enthalpy change of solution of silver nitrate in water is positive 22.6 kilojoules per mole. Suggest how the feasibility of dissolving solid silver nitrate in water changes with temperature. Okay, so we have silver nitrate, solid. Okay, when it dissolves in water, we get aqueous silver nitrate, right? We get Ag plus aqueous and NO3 minus aqueous, right? For feasibility, we have to look at the Gibbs free energy chain, which is delta G is equal to delta H minus T delta S. Now, what is the entropy change for this process? Okay, to understand feasibility, we'll have to look at the entropy change. What's the entropy change for this process? When you go from solid ions to aqueous ions, is the entropy change positive or negative? The entropy change would be positive, right? Because aqueous ions have a greater entropy than solids, right? So the entropy change is positive, which means that this delta G is equal to delta H minus T delta S can be written as delta G is equal to 22.6, that's the enthalpy change, minus the temperature times some positive value, right? Because the entropy change is positive. The entropy change is positive. Now, what would happen if I increase the temperature? The reaction become more feasible or less feasible? If I increase the temperature, this value is positive. So that means if I increase the temperature, this entire thing becomes more negative. Okay? This entire thing becomes more negative, right? So it will become more feasible. Delta G will become more negative, right? You're subtracting. This is a temperature is a positive value. This is a positive value. So this temperature times delta S, T delta S is positive. So higher temperature means this value is bigger. This value is bigger, and you're subtracting this. So that means you're subtracting a bigger value. So delta G is becoming more negative. So over here we would say that the reaction would become more feasible as the temperature increases, right? So feasibility increases, okay, as the temperature increases. Okay? And the reason why is because the delta S is positive. Delta S is positive. Therefore, minus T delta S and delta G become more negative. They become more negative as temperature increases. Okay? Here we have question number 4, which says in aqueous solution, iron 3 ions react with iodide ions as shown. A series of experiments is carried out using different concentrations of Fe3 plus and I minus as shown in table 4.1. Explain what is meant by overall order of a reaction. The overall order is the sum of the individual orders. Okay? Sum of the individual orders of each reactant in the rate equation. Okay? Of each reactant in the rate equation. Use the data in table 4.1 to deduce the order of the reaction with respect to Fe3 plus and with respect to I minus. So over here we have to first determine the order with respect to Fe3 plus, right? Because the concentration of Fe3 plus is changing in all 3 experiments, whereas the concentration of iodide ions is constant in experiments 1 and 2, right? So we can use experiments 1 and 2. If you use experiments 1 and 2, the concentration of Fe3 plus is increased by a factor of 3, okay? The concentration of Fe3 plus is increased by a factor of 3, whereas the concentration of iodide remains unchanged, and the rate, okay, and the rate changes by a factor of 3 as well. Okay, the rate changes by a factor of 3 as well. The rate changes by a factor of 3. So therefore, we can say that the order with respect to Fe3 plus is order 1, right? It's order 1 with respect to Fe3 plus. The rate changes by the same factor as the concentration. Now, to find the order with respect to iodide ions, right, we can just compare experiments 1 and 3, right? So in 1 and 3, what's happening is, that iron 3 plus is changing by a factor of 2, and the concentration of iodide ions is also being doubled. Okay, concentration of iodide ions is also being doubled, and the rate, okay, the rate is changing by a factor of 2.11 into 10 to the power minus 3 divided by 2.64 into 10 to the power minus 4. The rate is changing by a factor of 8. Okay, the rate is changing by a factor of 8. So here we can say that the concentration in experiments 1 and 3, okay, the concentration of Fe3 plus is doubled. Okay, the concentration of iodide ions is also doubled, but the rate changes by a factor of 8. Okay, the rate changes by a factor of 8. Now, what does that mean the order is with respect to iodide ions? Now, we know that the reaction is first order with respect to iron 3, which means that if I was to multiply the concentration of Fe3 plus by 2, the rate would also multiply by a factor of 2. We don't know the effect of iodide ions. However, we know that the overall effect on the rate is that it increases by a factor of 8. Now, if the rate doubles because of the Fe3 plus doubling, and overall the rate increased by a factor of 8, that means changing the concentration of iodide, okay, increase the rate by a factor of 4. Okay, it increased the rate by a factor of 4 because, again, doubling Fe3 plus means rate double, right? And then doubling I minus means that the rate quadrupled. Okay, it increased by a factor of 4, so the overall effect is 2 times 4, which is 8. Now, if doubling the concentration of iodide made the rate 4 times as much, that means that it is order 2 with respect to iodide. It's order 2 with respect to iodide. So order 1 with respect to Fe3 plus and order 2 with respect to iodide. So then the rate equation for this reaction is rate is equal to K times the concentration of Fe3 plus times the concentration of I minus squared. Use your answer to A part 3 and data from experiment 1 to calculate the rate constant for this reaction and include the units of K. So we're going to use the data from reaction 1. Okay, Fe3 plus 0.04, I minus is 0.02, and rate is 2.64 into 10 to the power minus 4. Okay, so we have rate, which is 2.64 to 10 to the power minus 4 is equal to K times the concentration of Fe3 plus, which is 0.04 times 0.02 squared. Okay, and then what we end up with over here is K as 16.5. Okay, and for the units, we have rate divided by concentration cubed, right? Rate divided by concentration to the power of 3. So that would be moles per dm cube per second. You always double check the units given in the question. Okay, so the units are given as moles per dm cube per second. Okay, sometimes they will be given in per minute as well. Okay, the units for rate are moles per dm cube per second divided by mole cube dm to the power of negative 9, right? So what do we end up with? We get K is 16.5 and then moles minus 2, right? 1 minus 3, minus 3 minus minus 9, so that would be dm to the power of 6 per second. Okay, so that's your answer. Describe qualitatively the effect of an increase in temperature on the rate constant and on the rate of this reaction. The rate and the rate constant, they both increase, right? The rate constant and the rate both increase. Okay, you don't have to explain it, but the explanation for this is as the temperature increases, right? As the temperature increases, the kinetic energy of the particles increases. So the particles are moving faster, right? And more particles have energy greater than or equal to the activation energy, right? So that means that the frequency of collisions increases and the frequency of successful collisions increases. Okay, so the rate of the reaction increases. In aqueous solution, iodide ions react with acidified hydrogen peroxide as shown. The initial rate of the reaction is found to be first order with respect to iodide, first order with respect to hydrogen peroxide, and zero order with respect to H+. Figure 4.1 shows a four-step mechanism for this reaction. Okay? So it's first order with respect to iodide, first order with respect to hydrogen peroxide, and zero order with respect to H+. Okay? Now using this mechanism, we have to determine the rate determining step, and we have to explain our answer. Again, the order with respect to a particular reactant tells you the number of moles, that react up to the rate determining step, up to the slow step, okay, the rate determining step. So, if it's zero order with respect to H+, that means 0 moles of H+ react up to the rate determining step. So then that means that step 1 must be the slow step. Okay, step 1 must be the slow step. Okay, up to the rate determining step. Okay, up until the rate determining step, we have 0 moles of H+. It can't be the second step or the third or the fourth, because in the second step we have H+. So if step 2 was the slow step, then we have 1 mole of H+ that's already reacted, right? So again, number of moles that react up to the slow step, we have 0 moles of H plus up to the slow step, so that means that the first step has to be the slow step, okay? Because there should be no H plus up to the slow step. This H plus has to come after, the H plus has to come after the slow step, okay? So the explanation for this is 1 mole of H2O2 and I minus react in step 1, okay? And H plus reacts after, okay? Identify a step in figure 4.1 that involves a redox reaction. Explain your answer in terms of oxidation numbers. Over here, step 3 is a redox reaction, okay? A very easy way to identify a redox reaction is when something is converted from a non-elemental form to its elemental form, right? Where iodine is going from its non-elemental form, right? The iodide ion, or in this case, the iodate, right? To iodine in its elemental form, right? What are the changes in oxidation number? In HIO, iodine is +1, okay? You can figure that out. Hydrogen is +1, oxygen is -2. 1 minus 2 is -1, which means that iodine must be +1. Okay, here iodine is -1, and then here iodine is 0, right? So iodine is being reduced from +1 to 0 and is being oxidized from -1 to 0, right? So in terms of oxidation numbers, right, that would be step 3. Okay, step 3, I is oxidized from -1 to 0, right? -1 in I minus and 0 in I2, and its I is reduced from +1, that's in HIO, to 0. Again, that's in iodine. Suggest the role of HIO in this mechanism. Explain your reasoning. So going back to the mechanism, okay, HIO is made during the mechanism and then it's used up in the next step. So it's made in step 2 and then used up in step 3. What do we call something that's made during the reaction and then used up during the reaction as well? This is called an intermediate. Something that is made during the reaction and then used up is called an intermediate. So it doesn't show up in the overall equation. Okay. So HIO is an intermediate. Okay. HIO is an intermediate. Why is it an intermediate? Because it's formed during the reaction, right? So that's in step 2 and then used up. Okay, and then used up. Okay, it's used up in step 3 in the next step. Here we have question number 5, which says methyl benzene can undergo different reactions as shown in figure 5.1. Draw structures in figure 5.1 for the possible organic products of the 3 reactions shown. So in reaction 1, methylbenzene is reacting with hydrogen in the presence of platinum catalyst. You can use nickel catalyst as well. This is the hydrogenation of benzene, right? The hydrogenation or the reduction of benzene. So we get rid of the benzene ring, okay, and we have that methyl group, okay? So we get a methyl cyclohexane, okay? We get a methyl cyclohexane, okay? We get rid of the benzene ring. So in reaction 2, we're reacting this guy with bromine in the presence of UV light. Okay, there's no catalyst, so we have free radical substitution. Okay, free radical substitution. We have substitution on the alkyl group. Okay, we have substitution on the alkyl group. So the CH3 becomes a CH2Br. The bromine replaces the hydrogen. Okay, no substitution on the ring. For that, we need a catalyst. Okay, so then this would be this, and then a CH2Br. Okay, so free radical substitution. And then reaction 3, we have electrophilic substitution, right? Methyl benzene is reacting with bromine in the presence of FeBr3 catalyst. We get 2 different products because the methyl group is 2,4 directing. Okay, methyl group is 2,4 directing. So we get a bromine on carbon number 2. That's the carbon next to the methyl group. And then we also get a bromine on carbon number 4 relative to the methyl group, right? So that's what we mean by 2,4 directing, means that the methyl group will determine where the bromine will go. So if it's 2,4 directing, it will go on the carbon next to it and the carbon directly opposite. Complete table 5.1. What's the type of reaction for reaction 1? Reaction 1 is a reduction reaction, okay, also referred to as hydrogenation. Okay, also referred to as hydrogenation. And then the mechanism for reaction 2 is free radical substitution. Okay. So type of reaction for reaction 1 is reduction. And then the mechanism for reaction 2 is free radical substitution. When methylbenzene reacts with an electrophile, a substitution reaction occurs. No addition reaction takes place under these conditions. Explain why no addition reaction takes place. Now, the key thing to remember is that benzene, just like alkenes, okay, is unsaturated. Okay, benzene is unsaturated just like alkenes. However, in benzene, the electrons are delocalized. Okay, in this pi bond, in this delocalized pi bond. So because they're delocalized, the electrons are occupying a larger space. There's lesser repulsion, so the electrons are more stable. If they're more stable, okay, they're happier being in this pi bond. They're happier being in this pi bond because they have much more space than they are in this pi bond. So alkenes undergo addition generally, but benzene generally does not undergo electrophilic addition. Okay, benzene does not generally undergo addition reactions. Okay, it can undergo addition reaction, but usually it doesn't. Okay, usually it doesn't. Okay, so over here we can say that the delocalized pi electron system, okay, the delocalized pi electron system, or you can say the delocalized pi bond, makes the benzene ring, okay, benzene more stable. Okay, therefore it does not undergo addition. Okay, it does not undergo addition. Okay, because this pi electron system is preserved. It's preserved if it undergoes substitution. Okay, if you had addition, then you wouldn't have this pi electron system anymore. Okay, this pi electron system, I'll write this down. Okay, you should mention that as well. Actually, it's preserved. It's preserved when benzene undergoes substitution. Okay, when benzene undergoes substitution. Okay, these electrons are happy in this delocalized system. They want to remain delocalized. Okay, they want to remain delocalized. The reaction of methylbenzene with thionyl bromide, SOBr2, in the presence of an iron 3 bromide catalyst, FeBr3, is shown in figure 5.2. The mechanism of this reaction is similar to that of the bromination of benzene. The first step of the mechanism generates the electrophile as shown. The reaction of methylbenzene with SOBr plus ions is shown in figure 5.3. Complete the mechanism in figure 5.3. Include all relevant curly arrows and charges. Draw the structure of the organic intermediate. Okay, so for this mechanism, over here, you have to show the curly arrow from the ring to the positively charged sulfur atom. Okay, curly arrow from the ring to the positively charged sulfur atom. Okay, make sure you show it from this circle over here. Okay, from the ring. Okay, don't show it from the carbon. Show it from the ring. Okay, and then you get a carbocation intermediate. Okay, you get a carbocation intermediate. Okay, you show this ring open up towards. Show the ring open up towards the carbon where this sulfur is bonding. Okay, towards the carbon where the sulfur is bonding. We have to show the hydrogen atom as well. Okay, so we have SOBr. Okay, the reason I'm showing it on carbon 2 is because in the question they've shown the SOBr on carbon number 2. Okay, shown the SOBr on carbon number 2, so your mechanism has to be consistent with that. Okay, and then in the second step, okay, this bond between the carbon and the hydrogen breaks, and both the electrons, okay, go back into the ring. So you have to show a curly arrow from the bond back into the ring. Okay, so the pi electron system reforms, and we end up getting our final product. And obviously over here we also get H plus, right? H plus is removed. Okay, and this bond breaks, H plus is removed. Okay, and then this H plus can react with FeBr4 minus. Okay, I'll write that down even though they're not asking for it, but I'll still write it down. Okay, the H plus reacts with FeBr4 minus, and we end up regenerating the catalyst, that's FeBr3, and we get HBr, okay, which is our other product. Okay, HBr is the byproduct of this reaction. The reaction shown in figure 5.2 produces a small amount of byproduct P with the molecular formula C14H14OS. Suggest a structure for byproduct P. So what they're saying over here is that when methylbenzene reacts with SOBr2, we end up getting a 14 carbon product. Okay, we end up getting a 14 carbon product. So I'll write this down, right? They're saying when methylbenzene, reacts with SOBr2, we end up getting a 14 carbon product. Okay, C14H14OS. So that means that we must have two methylbenzene rings. Okay, we must have two methylbenzene rings. So we have methylbenzene, we have the S double bond O, and we have no bromine here. So that means that the other bromine, okay, we get a methylbenzene ring over here, and we get a methylbenzene over here. Okay, we get a methylbenzene here and a methylbenzene here. So we get this guy. Okay, so that is the structure for byproduct P. Okay, acyl bromides RCOBr can be synthesized by the reaction of a carboxylic acid and SOBr2. This is a similar reaction to the synthesis of acyl chlorides using SOCl2. Given equation for the reaction between ethanoic acid and SOBr2. Okay, so what we have here is ethanoic acid, CH3COOH, okay, reacts with SOBr2. Okay, we get an acyl bromide instead of an acyl chloride. So we get CH3COBr, and then we get SO2 and HBr. Okay, SO2 and HBr. Okay, so again, the bromine replaces the OH, right? The bromine replaces the OH, and we get SO2 and HBr. If this is SOCl2, we get SO2 and HCl. Okay. Suggest the relative ease of hydrolysis of acyl bromides, acyl chlorides, and alkyl chlorides. Explain your answer. Now, for the ease of hydrolysis, okay, when these guys undergo hydrolysis, the bond between the carbon and the halogen is broken. Okay, the bond between the carbon and the halogen is broken. Now, if you have an acyl group, if you have a C double bond O, right, this guy has an electron withdrawing effect. This guy has an electron withdrawing effect because oxygen is electronegative. That weakens the bond. Okay, that weakens the bond. So we know that the acyl chloride and the acyl bromide will react more readily than the alkyl chloride. Okay, so the hardest to hydrolyze will be the alkyl chloride. Okay, the hardest to hydrolyze will be the alkyl chloride. Okay, now the easiest to hydrolyze, okay, will be the acyl bromide. Why? Because the carbon bromine bond is weaker. Down the group, the size of the atoms increases, right? Number of shells increases, bond length, shielding increases, bond length increases, right? So that means the bond is weaker between carbon and bromine compared to carbon and chlorine. Okay, so the easiest to hydrolyze will be the acyl bromide, followed by the acyl chloride, followed by the alkyl chloride. Okay, now over here we know that that the CX bond is weaker, okay, in acyl chlorides and acyl bromides, okay, acyl bromides, than in alkyl chlorides, okay, due to the electron withdrawing effect, due to the electron withdrawing effect of the electronegative oxygen atom, okay, electronegative oxygen atom. We also know that the CBr bond, okay, CBr bond is weaker than the CCl bond, right? Why? Because as bond energy decreases down the group, okay, bond energy decreases down the group, right, down the group as bond length increases, okay, as bond length increases. So here we have question number 6, which says perindopril is a drug used to treat heart disease. State the number of chiral carbon atoms present in one molecule of this compound. So here we're going to start on the left, right? This is a CH3, CH2, because these aren't chiral carbons. Here we have a double bond, so that's not chiral. This carbon over here is chiral, right? So that's one. This carbon here is chiral, right? A chiral carbon is a carbon that's bonded to 4 different atoms or groups of atoms, right? So chiral, chiral, right? Both of these have a hydrogen. This carbon over here is a chiral carbon. This one here, and then this one here, right? All the other carbons on the rings are CH2s, right? All the other carbons are CH2s on the ring. And again, these ones have double bonds, so they're not chiral carbons. The number of chiral carbons here is 5. Suggest one benefit and one disadvantage of producing a drug such as perindopril as a single pure optical isomer. Now, the benefit of this is that we only want a particular optical isomer for medical use. Okay, so if you're producing a medicine or a medicinal drug like this guy over here, okay, you want that particular optical isomer that actually works for treatment, right? You don't want the other optical isomers. So the benefit is that, so the benefit over here is that this particular isomer, okay, will be the one that we're going to need for its biological activity, right? So the benefit is that this particular pure optical isomer will have lesser side effects, right? Will have fewer side effects, right? And it'll be more effective, right? It'll be more effective for its therapeutic or medical benefits, okay? More effective for its medical purpose, right? The disadvantage, of course, is that if you want to produce a single pure optical isomer, right? Let's say you have a mixture of optical isomers, right? Separation is needed, right? So the disadvantage is that the desired isomer, okay, the desired isomer needs to be separated, okay, okay, which can obviously be time consuming and costly, right? Which can be costly and time consuming. Okay, this is a basic sort of a general knowledge type of a question, okay? It can be costly or time consuming. Okay. One of the things that we can use to obtain a single pure optical isomer is a chiral catalyst, okay? A chiral catalyst will selectively result in the production of the desired optical isomer, okay? They can be organic catalysts such as enzymes, or they can be metal-based inorganic catalysts as well. Name all the functional groups present in perindopril. Okay, so all the functional groups here, well, we have an ester, right? We have an ester linkage. We have an amine, specifically it's a secondary amine. Okay, we have an amide, the nitrogen is bonded to 3 carbons, so that's a tertiary amide, and we have a carboxyl group. So over here we can say we have an ester linkage. Okay, so ester, we have a secondary amine. Okay, you can just say amine as well, but I would personally say secondary amine, okay, to be more specific. So secondary or 2-degree amine. You have a tertiary amide, and you have a carboxyl group. Okay, you can say carboxyl or carboxylic acid. But the name of the functional group is actually the carboxyl group. A sample of perindopril is hydrolyzed with hot aqueous acid. Draw the structures of the 3 organic products of the complete acid hydrolysis of perindopril. So we're first going to look at the compound here, right? We have this compound perindopril. So I'm just going to make a copy of this. Now we go back down. Okay. Now what happens when this compound is hydrolyzed? Which functional groups will react when this compound is hydrolyzed with hot aqueous acid? You guys should know that when this compound is hydrolyzed, okay, it's the ester linkage, okay, it's the ester linkage and the amide that undergo hydrolysis, right? Now when esters undergo hydrolysis, this bond between the C double bond O and the oxygen breaks, and for amide it's the bond between the C double bond O and the nitrogen. So when this bond over here breaks, what do we end up with? Well, we end up making ethanol, right? So we have ethanol, that's one of the products. The other product that we have is this guy over here, right? This guy will become a carboxylic acid, right? Because again, it's a C double bond O, right? So this will become a carboxylic acid. and this C double bond O will also become this carbon will also become a carboxyl group, right? So this will also become a carboxylic acid. We draw that out, right? We have an OH, we have a C double bond O, then we have this carbon that's bonded to this chain down here, right? This branch, 1, 2, 3 carbons. Then we have an NH. Okay. Now because it's acidic hydrolysis, I would say that this would become an NH2 plus. Okay, this would become an NH2 plus, right? Because you're going to get the salt of the amine in acidic conditions. And in some cases, they do just accept you saying NH. Okay, they do just accept you saying NH. However, because we have acidic conditions, the amine is basic, right? The amine group is a base, so it's going to accept a proton. So this is a better answer, okay? In some cases, they'll only accept this as an answer, okay? Because it's a more accurate answer. In this particular marking scheme, they accept you leaving it as NH, okay, but this would be a better answer. And then you have another carbon with a methyl group. Then you have the C double bond O, that becomes a carboxylic acid, right? So this guy becomes a CO2H. And then lastly, we have this guy over here, right? We have this guy over here, right? This will become what? Well, let's just first draw out the ring, right? So we have a 6 carbon ring. We have a 6 carbon ring like this, right? That's this 6 carbon ring. Then we have another 1, 2 carbons, right? And then we have a nitrogen. So we have 1, 2, then we have a nitrogen. That nitrogen is bonded to this carbon, right? That will become an NH2 plus again, right? Because it's acidic conditions, right? So acidic hydrolysis, we get the salt of the amine, right? We get the salt of the amine. So this will become NH2 plus. And then this carboxylic acid group will remain unchanged, right? This carboxylic acid group will remain unchanged. So on this carbon here, right, that's bonded to the nitrogen. So on the carbon bonded to the nitrogen. So we have this C double bond O and then OH. Okay. So you have to be careful when drawing this. All right. As I said again, in this particular case, they do accept you just saying NH, but a better answer is NH2 plus because again, it's acidic conditions. So you end up making a salt of the amine, right? Because the amine is a base, it accepts a proton. Question number 7 says, explain why phenol is brominated much more easily than benzene is brominated. So this question is basically asking why is phenol much more reactive towards electrophiles than benzene is. And the reason why is because the delocalization, right, the delocalization of the lone pair of electrons, okay, the lone pair of electrons in the p orbital, okay, in the p orbital of the oxygen atom in phenol results in an increase in electron density. Okay, it results in an increase in electron density in the ring, making phenol much more reactive towards electrophiles. Okay, making phenol much more reactive towards electrophiles, right? Because again, the bromination of phenols and the brominations of benzene are electrophilic substitution reactions. Okay, they're electrophilic substitution reactions. Now, because there's a greater electron density in the benzene ring, right? There's a greater electron density in the benzene ring. In the case of phenol, it'll attract electrophiles more strongly, right? Electrophiles are electron pair acceptors. Okay, they want electrons. The greater the electron density, the more strongly something will be attracted to an electrophile. Okay, that's why phenol is much more reactive towards electrophiles because it has a greater electron density in the ring. Iodine monobromide reacts with benzene in the presence of an AlBr3 catalyst. Explain whether the organic product will be bromobenzene or iodobenzene. Explain your answer. Now again, this is similar to the reaction of benzene with bromine, right, which is an electrophilic substitution reaction. Okay, electrophilic substitution reaction. So the question here is, which will be the electrophile? Will it be the iodine or the bromine? Now we know that down the group, electronegativity decreases. Okay, down the group, electronegativity decreases. So iodine is less electronegative than bromine. Okay, iodine is less electronegative, so it's partially positive. Bromine is partially negative, right? So the iodine will therefore be the electrophile in this reaction, right? The iodine will be the electrophile in this reaction. Okay, this guy will attract electrons more readily, right? It'll accept a pair of electrons more readily. So over here, we're going to say iodobenzene, okay, will be the organic product. Okay, the reason why is because iodine is less electronegative than bromine. Iodine is less electronegative than bromine. Okay, therefore it will be the electrophile. Okay, it will be the electrophile. Okay, I'll write down the equation also. What will happen here is that this IBr will react with the catalyst AlBr3, right? And what do you end up getting? You're going to end up getting I plus and AlBr4 minus, right? AlBr4 minus. So this bond between the iodine and the bromine will break, but the electrons will go to the bromine because it's more electronegative. So you end up with this electrophile, right? The I plus, this iodine 1 plus ion, right? This is what's going to react with the benzene to make iodobenzene. Figure 7.1 shows some reactions of phenol. Give an equation for the reaction of phenol with solid sodium. So phenol, which is C6H5OH, reacts with sodium metal, and you get a salt and you get hydrogen gas, right? Sodium is a test for the OH group, right? Sodium is a test for the OH group. So this hydrogen over here from the OH group ends up becoming hydrogen gas, okay? And we have this salt, which is called sodium phenoxide, okay? Sodium phenoxide. Draw the structure of the organic product R formed when phenol reacts with an excess of aqueous bromine. Now, when phenol reacts with an excess of aqueous bromine, we get 2,4,6 tribromophenol, right? So this is phenol, and then we get 3 bromines, right? At the 2, the 4, and the 6 position. So we get 2,4,6 tribromophenol. The observation in this reaction is that we see decolorization of aqueous bromine, right, from orange to colorless, okay, or brown to colorless. We see decolorization of aqueous bromine, and we see a white precipitate. We see a white precipitate of this guy, 2,4,6 tribromophenol. State the reagents and conditions for reaction 1 and reaction 2. Reaction 1 is the reaction of phenol to form 4-nitrophenol, right? 4-nitrophenol again. Phenol is carbon 1, 2, 3, and then 4. So 4-nitrophenol. For this, we're going to use dilute nitric acid, okay, at room temperature. So we use dilute nitric acid at room temperature, okay. And then for the second one, okay, we're making an azo dye. Okay, we're making an azo dye. So for this, we're going to use a diazonium salt, right? We're going to use a diazonium salt. You guys should remember that we use diazonium salts, okay. We can react them with phenol to make azo dyes, okay. And this reaction has to be carried out between 0 and 10 degrees Celsius, okay, between 0 and 10 degrees Celsius. So a suitable temperature would be 5 degrees Celsius, okay, 5 degrees Celsius, and it has to be carried out in alkaline conditions, okay. So we need aqueous alkali, okay, we need aqueous alkali. So it has to be carried out in alkaline conditions. So what do we have here? For reaction 1, we're going to use dilute nitric acid, okay, dilute nitric acid. This reaction takes place at room temperature, and then the next reaction we're making an azo dye. So for that we're going to use a diazonium salt, C6H5N2+. Okay, that's the benzene diazonium ion in alkaline conditions. Okay, and we want to maintain a low temperature, right? Because the diazonium salt is sensitive to heat. Okay, so a temperature of 5 degrees Celsius. Describe the difference in reactivity between chloroethane and chlorobenzene with aqueous hydroxide. Explain your answer. Now, when chloroethane, right, which is CH3, CH2, Cl, reacts with aqueous sodium hydroxide, right, or aqueous hydroxide, we end up getting ethanol. Okay, we end up getting ethanol as the organic product, right? CH3, CH2OH, and we get Cl minus, right? This is when you have aqueous sodium hydroxide. So what's happening here is the hydrolysis of the carbon-chlorine bond, right? It's referred to as hydrolysis of halogenoalkanes. Okay. Now, in the case of chlorobenzene, right, hydrolysis does not occur. The reason why hydrolysis doesn't occur is because we have a lone pair of electrons in the p orbital of chlorine, right, and that delocalizes into the benzene ring. What that does is that it increases the electron density between the carbon and the chlorine, right? Increases the electron density between the carbon and the chlorine. It makes the carbon-chlorine bond stronger, right? It makes the carbon-chlorine bond stronger, and therefore this carbon-chlorine bond does not break, right? Because it has like a partial double bond character, right? You have a sigma bond and then you have this partial pi bond character, okay? So the strength is sort of somewhere in between a single and a double bond, okay? That's one way to think about this. So we can say is that in chlorobenzene, right? Okay, in chlorobenzene, what happens is, right, the lone pair of electrons, okay, the lone pair of electrons in the p orbital, okay, in the p orbital of the chlorine atom, right, delocalizes, okay, delocalizes into the benzene ring, okay, delocalizes into the benzene ring, okay, this makes the carbon chlorine bond stronger, right, making the carbon chlorine bond stronger, okay, and therefore less reactive, okay, less reactive. So therefore chlorobenzene will not undergo hydrolysis, right? So chlorobenzene is less reactive. Compound T, C5H9O2Cl, is a useful synthetic intermediate. Figure 8.1 shows some reactions of T. So we have compound T undergoing certain reactions. The first part says give the systematic name for T. Give the systematic name for T. Now T over here is an ester. Okay, T over here is an ester. So for the naming of T, okay, what we're going to do is we're going to name it in two parts, right? How do we name an ester? Well, we start with the alcohol part. So we have this 2-carbon alcohol, right? So this ester was made using ethanol, right? So we have 1, 2. So that would be ethyl, right? That would be the first part of the name, ethyl. And then we have the carboxylic acid part, right? Which is 1, 2, 3 carbon. So that's propanoate, ethyl propanoate. However, we also have a chlorine on this carbon. So how would we name this? Well, if this was ethanol, right? So that would be the ethyl part. And then this compound is propanoic acid, but we have a chlorine, right? So instead of having a 3-carbon acid, just propanoic acid, we also have a chlorine here. And the chlorine is on carbon number 3, right? The acid gets carbon 1, and this is carbon 2, it's carbon 3. So we have 3-chloropropanoic acid, okay? So we have ethanol and 3-chloropropanoic acid that react to make this ester. So how do we name this? Well, we write the alcohol part first, so that's ethyl. And then the acid part would be 3-chloropropanoate. Okay, 3-chloropropanoate. Next part says draw the structures of W, X, Y, and Z. How do we draw the structures of W, X, Y, and Z? Okay, so in the case of W and X, right, W and X form when this compound undergoes alkaline hydrolysis, right, alkaline hydrolysis. So what happens? Well, the ester linkage is hydrolyzed, okay, and this chloroalkane is also hydrolyzed, right? We also have a chloroalkane here, so this group is also hydrolyzed, right? So aqueous sodium hydroxide, this becomes an alcohol, right? This becomes an alcohol. So we have OH, and then we end up getting a salt of the carboxylic acid, right? Because alkaline conditions, and then we also get ethanol. Okay, we also get ethanol. We get this 2-carbon alcohol. We get the salt of the carboxylic acid because alkaline conditions, and the chlorine, the chloroalkane ends up becoming an alcohol. Okay, we can also react T with something in step 1, right? To make this compound here, we're going to use KCN and ethanol, right? This is nucleophilic substitution. Nucleophilic substitution, right? What are we doing here? We're substituting the chlorine for cyanide, right? We're making a nitrile. And then we're reacting this guy with HCl aqueous. So this is acidic hydrolysis. So again, the ester linkage is hydrolyzed, okay? And the nitrile is also hydrolyzed, right? Nitrile is also hydrolyzed. So the C triple bond N breaks, right? The C triple bond N will also break. And this carbon will become a carboxylic acid. But now, obviously, because we have a nitrile, right, we have an extra carbon over here, okay? So what do we have? We have this guy becomes a carboxylic acid, right? That's the nitrile. And then we have this and this and then this. We get a carboxylic acid here, and we get ethanol. And then lastly, this compound is reacted with something in step 2 to produce compound Z. Now, what do you guys think compound Z is based on the molecular formula? Okay, look at the molecular formula of this compound here and then compound Z. If you looked at the molecular formula here, you'd realize that this guy over here has 3 plus 2, 5, and then 2 and then 2. So that is 9 hydrogen atoms, okay? So this guy over here is C6H9NO2, right? And over here you have C6H13NO2. So you have 4 more hydrogens. So this is reduction, okay? Reduction of nitriles to form an amine, okay? Reduction of nitriles to form an amine. So this guy over here will become a CH2NH2, right? Become a CH2NH2. This is the reduction of nitriles. Okay? This is the reduction of nitriles. So what do we end up getting? Well, we end up getting an NH2 here, right? We end up getting an NH2. So this carbon becomes an NH2. Then we have another 1, 2, 3 carbons. So 1, 2, 3 carbons. And we have this ester linkage. And we have the rest of the compound. Okay. So for reduction of nitriles, you can use lithium aluminum hydride in dry ether. So LiAlH4 in dry ether. Or you can use hydrogen and nickel. Okay, you can use either one. Okay, so in step 1 we were making the nitrile. Okay, in step 1 we were making the nitrile, and then in step 2 we're reducing that nitrile. Okay, so for step 1 we're going to use KCN and ethanol and heat. Okay, KCN and ethanol and heat. Okay, and then for step 2 we're using hydrogen and nickel. Okay, and heat. Or you can use LiAlH4 in dry ether. Okay, and then heat. Part C says the proton NMR spectrum of compound T C5H9O2Cl in CdCl3 is shown in figure 8.2. So we have the NMR spectrum, okay, the proton NMR spectrum for this compound T. The question says, suggest why CdCl3 is used as a solvent instead of CHCl3 for the proton NMR spectrum. Well, because it has the deuterium, right, which is hydrogen 2, right? And remember, any isotope with an even number of nucleons does not show up in the NMR spectrum, right? It does not show up in the NMR spectrum. So CdCl3, right, does not have a peak, okay, does not have a peak in the NMR spectrum, right, in the proton NMR spectrum. Okay, the reason why is because deuterium, right, deuterium, which is the hydrogen 2 isotope, right, has an even mass number, right, or an even number of nucleons, okay, an even nucleon number or even mass number. Complete table 8.2 for the proton NMR spectrum of T. Okay, so now going back to the compound, right? So the first question is, okay, which of these protons over here is responsible for the peak at 1.2? Okay, 1.2 is simply the alkane proton, right? 1.2 is the alkane proton. So which Which proton is that? I'm going to label these protons A, B, C, and D. Okay, A, B, C, and then D. Now, proton A, okay, proton A over here, right, which are these three protons over here, right? So we have a CH3, right? These guys are just bonded to a CH2. These guys are bonded to a CH2. So this is your alkane proton, right? So this peak at 1.2, the peak at 1.2 is because of proton A, right? We know that because it's an alkane proton, it's bonded to a CH2, and we also know that it has a triplet splitting pattern, right? Because the neighboring carbon has two protons. Remember, the splitting pattern is the number of neighboring protons plus 1. So over here we have 3 protons. The neighboring carbon has 2 protons. The neighboring carbon has 2 protons. So the splitting pattern is 2 plus 1, which is 3. Okay, splitting pattern is the number of neighboring protons. So that's 2 hydrogen atoms in the neighboring carbon plus 1. So the splitting pattern is a triplet. Okay. Now what about HB? Well, HB must be a quartet. Okay, HB must be a quartet, right? Because the neighboring carbon has 3 protons. The neighboring carbon has 3 protons, so it will undergo a splitting pattern of 3 plus 1, which is 4. Okay, that's a quartet. So this is the only quartet here. That means that this must be carbon B, even without looking at the shift. Okay, we can confirm this by looking at the shift, but even without looking at the shift, we know that this must be proton B. Why? Because again, the neighboring carbon has 3 protons, so the splitting pattern is 3 plus 1, which is 4. Okay, and this carbon is bonded to an oxygen. Okay, this carbon is bonded to an oxygen, so we can confirm that the shift will be in the range 3.2 to 4 parts per million. Okay, it will be in the range 3.2 to 4 parts per million, and that is consistent with what we said here. Okay, proton C over here, okay, is a CH2. Okay, it's a CH2 next to a C double bond O. A CH2 next to a C double bond O. So we go here, we have a CH2 next to a C double bond O, so it should shift in the range 2.2 to 3 parts per million. Okay, 2.2 to 3 parts per million. So that must be this one, right? That must be this one. So this is proton C, and then proton D is this guy, right? That's the CH2 next to the chlorine. Okay, it's a CH2 next to the chlorine. So again, if we look at the table, right, we have a CH2 next to an electronegative atom like chlorine. So that should shift in the range 3.2 to 4, right? So that shifts in the range 3.2 to 4 parts per million. Okay, and over here you can see the splitting pattern, right? For C and D, we have 2 triplets, right? We have 2 triplets. So whenever you see a triplet quartet, we know we have a CH3, CH2, right? Why? Because the CH3, in this case that was proton A, right, is split into 3, by the neighboring 2. Okay, it's split into 3, by the neighboring 2, and the CH2 over here, is split into 4, it's split into 4 by the neighboring 3, okay, and then here for C and D we have a CH2, right? We have two peaks, okay, with the same area, same height, okay, in this case, and same relative area, and they're both triplets. So this, we can say that proton C, okay, proton C is split into 3 by the neighboring 2, and then proton D is also split into 3 by the neighboring 2. All right. So we have to complete the table 8.2 for the proton NMR spectrum of T. So at 1.2 we had the alkane proton, right? Alkane proton over here. Okay, the splitting pattern in this case was a triplet. Okay, the splitting pattern was a triplet. Go back to the spectrum, right? Splitting pattern is a triplet, and the number of protons is 3, right? The number of protons is 3, so that's the relative peak area, right? Proton B is an alkyl next to an oxygen atom, right? The splitting pattern is a quartet. It's a quartet, right? And the number of protons is 2. For C, again we have 2 protons. Okay, it's alkyl next to a C double bond O. Okay, that's your environment. Alkyl next to a C double bond O. And then for the last one, proton D, it's an alkyl next to an electronegative atom, right? In this case, that's the chlorine atom. Okay, and the splitting pattern again for D is a triplet. Okay, so over here, I'll just write this down. Okay, you have the alkane proton, The splitting pattern was a triplet, right? That was your CH3 group. The number of protons was 3. Then we had the 2.8 is alkyl next to C double bond O. Alkyl next to C double bond O. That was also a triplet. The number of hydrogen atoms was 2, right? That was a CH2. All the others are CH2s, right? We had a 3.9, that was a CH2 next to an oxygen atom, okay, next to an oxygen atom, or you can just say electronegative atom. That was a quartet, right? That was a quartet. And then we have a CH2 next to a chlorine atom. That was also a triplet, okay? That was also a triplet. So all of them were triplets except this one, which was a quartet, right? And you have to explain the splitting pattern at 3.9. At 3.9 we had a quartet, right? The reason why is because the neighboring carbon, okay, the neighboring carbon had 3 hydrogen atoms, okay? So 3 hydrogen atoms, okay? Or you can say 3 hydrogen atoms, or you can say 3 protons on the neighboring carbon atom, okay? On the neighboring carbon atom. Here we have question number 9, which says define standard cell potential. Okay. Standard cell potential is the potential difference. It is the potential difference between the cathode and anode. Okay, it is the potential difference between the cathode and the anode of a cell, okay, under standard conditions. Under standard conditions. Okay, in this case, the standard conditions are 298 Kelvin, 1 atmosphere of pressure, right? 1 atmospheric pressure, and we're going to use 1 mole per dm cube solutions, okay, of the electrolytes. An electrochemical cell is set up to measure the standard cell potential of a cell consisting of an Fe3 plus Fe2 plus half cell and a chlorine chloride half cell. Draw a labeled diagram of this electrochemical cell. Include all necessary substances. It is not necessary to state the conditions used. So when we have an equilibrium between 2 ions, okay, we're going to use a platinum electrode. And when we have a non-metal, okay, with its ion, we're again going to use platinum as the electrode, okay. We're using a platinum electrode in both the half cells, okay. The only time we're not going to use an inert electrode, the only time we don't use an inert electrode is when we have a metal itself involved, okay, not the ion, but the element itself, okay. Like, so for example, if you have iron metal as the element, right, then you would use an iron electrode, okay. So what do we have here? Well, we have a platinum electrode, okay. I have a platinum electrode here as well, right, like this. We have a wire connecting these two. We have a voltmeter that you have to show here, okay, like this, okay. For this solution, okay, we're going to go with the iron 3 and iron 2 half cell. So we have Fe3 plus aqueous, right, should be 1 mole per dm cube. They've said that you don't have to specify the conditions used, okay. It is not necessary to state the conditions used, but I'll still use it. Why? Because it's good to know, right? They can ask for it. And if they don't say it, it is not necessary to state the conditions used, then you have to state them, okay. Unless they say that you don't have to, you have to state them, okay. And then in the other half cell, right, we have a chlorine chloride half cell. We need a gas delivery system, right? We need a gas delivery system for the chlorine. So we have something like this, right? We have something like this, and we have this, right? And then we're going to have chlorine gas, right? And again, you don't have to state the conditions, but I'll state them, right? It has to be at 298 Kelvin and 1 atmosphere of pressure, right? And then our solution will be 1 mole per dm cube chloride ions, right? Need a 1 mole per dm cube solution of chloride ions, right? So aqueous chloride ions. I should mention aqueous as well. Okay, aqueous, aqueous, and aqueous, right? We have the voltmeter. and then we have the platinum electrodes. We have the platinum electrodes, and then of course we shouldn't forget the salt bridge, right? This is what completes the circuit. This is what completes the circuit. We have the salt bridge. Salt bridge. The cell reaction for the electrochemical cell in part B is shown. Calculate the standard Gibbs free energy change in kilojoules per mole for this cell reaction. Now you guys should know that the standard Gibbs free energy change delta G is equal to minus NFE, okay, minus NFE, where E is the standard cell potential, okay, N is the number of moles of electrons, and F is Faraday's constant, right? Now here, in this particular case, how many electrons do we have? Well, N should be 2. So in this particular case, we have Cl2 reacting with 2 moles of Fe2 plus to give us 2 moles of Fe3 plus and 2 Cl minus, okay? So we need to figure out N, which is the number of moles of electrons, right? So we have Fe2 plus is undergoing oxidation to form Fe3 plus and electrons, and Cl2 is the oxidizing agent and undergoes reduction to form 2Cl minus, okay? These are our half equations. The half equation above has to be balanced, right? Because we have 2 moles of Fe3 plus, 2 moles of Fe2 plus, and then 2 electrons. So here N, the number of moles of electrons is 2, right? 2 moles of electrons are being exchanged. Cl2 is gaining 2 electrons, and Fe2 plus, we have 2 moles, okay? So they're losing 2 electrons. So then N is equal to 2, okay? N is equal to 2 here. So then we can say that delta G is equal to minus 2 times 96,500 times the standard cell potential, which is 0.59, okay? That will give you negative 113,870 joules per mole, okay? This value will come out in joules, right? Because we're using SI units here, right? We're using SI units. And then to convert this to kilojoules per mole, we just have to divide it by 1,000. So the answer is negative 113.870 kilojoules per mole, or we can just say negative 114 kilojoules per mole, right? To 3 significant figures. All right. Moving on. Another experiment is set up using the same electrochemical cell. In this experiment, the Fe2 plus concentration is 0.15 mole per dm3. All other concentrations remain at their standard values. The Nernst equation is shown. Use the Nernst equation to calculate the electrode potential for the Fe3 plus Fe2 plus half cell in this experiment. Okay. Now in the Nernst equation, okay, this numerator, the oxidized species is the species with the higher oxidation number, okay? Species with the higher oxidation number, and the reduced species is the species with the lower oxidation number, okay? What they're saying here is that they're changing the concentration of Fe2 plus to 0.15 mole per dm3. The concentration of Fe3 plus remains the same, right? So that's 1 mole per dm3, right? That's a standard value. So we can say that E is equal to E naught, right, which is 0.77, 0.77 plus 0.059 over Z, because Z over here is 1, because Z is 1. So you can write down the half equation, Fe3 plus E minus gives you Fe2 plus, right? So we have 1 electron in this half equation, right? We have 1 electron in this half equation. So Z is equal to 1. And then log of the concentration of the oxidized species, that is the species with the higher oxidation number, that's Fe3 plus, okay, that remains unchanged. So that's just 1 divided by the concentration of the species with the lower oxidation number, that's Fe2 plus, okay, so that's 0.15 mole per dm3 in this particular case, okay, and if you calculate that, you get 0.82 volts. So you get a higher standard reduction potential, and that's expected, right? Over here, you have a greater concentration of Fe3 plus. In other words, you decrease the concentration of Fe2 plus, which means that the equilibrium will shift to the right. The equilibrium will shift to the right, okay? So the reduction of Fe3 plus will be more favored. Okay, the reduction of Fe3 plus will be more favored. So therefore, you're going to get a more positive standard reduction potential, okay? So 0.82 or positive 0.82 volts. Use your answer to D part 1 to calculate the EMF of the cell for this electrochemical cell. Okay, now in this particular cell, what did we have? We had Cl2 reacted with Fe2 plus, okay, and we had 2 Fe2 plus, and that gave us 2 Fe3 plus and then 2 Cl minus, right? So in this particular case, what do we have? Well, in this particular case, Cl2 was undergoing reduction. Cl2 was undergoing reduction, right? So that was the cathode, right? This was the cathode, right? The chlorine chloride half cell, or the electrode at which chlorine was undergoing reduction, right? So that was the cathode, and then the electrode where iron was being oxidized, right? That was the anode. Now you guys should know that the EMF of the cell is the electrode potential at the cathode minus the potential of the anode, right? So we have potential of cathode minus potential of anode. Now what you've done here, okay, the cathode remains unchanged. Okay, the cathode remains unchanged. The cathode remains unchanged. So this remains the same. Okay, this remains the same. But the anode was initially 0.77. The anode was initially 0.77. Now the anode has increased. Okay, it's increased from 0.77, it's gone to 0.82. So the anode has become more positive, right? The electrode potential at the anode has increased by 0.05, right? Now, they had told us that the standard cell potential was 0.59. The standard cell potential, okay, the standard cell potential was 0.59. So I'll write that down. The standard cell potential was positive 0.59 volts, right? But now in this case, the anode, okay, the electrode potential at the anode has increased by 0.05. That means that the cell potential, you're subtracting a bigger value. You're subtracting a bigger value. The cell potential will decrease by 0.05. So we can say that the EMF of the cell is 0.59 minus 0.05, which is 0.54 volts. So that's your answer.